Here we have a series circuit. There's a 9-volt cell in series with a 2K resistor and a 1K resistor. We know that it's a series circuit because there aren't any branches in the circuit. All the charge has to flow in one path all around in the circuit. The components follow one another, one after the other. We can liken this series circuit to this picture shown here. Each of the blue circles stands for a group, a coulomb of moving charge. Wires throughout the circuit contain charge. They contain positive and negative charge. In the case of electricity, it's the negative charge, the electrons, which can be moved. Some of them can be moved. And this moving charge forms electric current. We can imagine these groups of charge, these blue circles, moving clockwise around in the circuit. Out of the positive terminal of the cell, round through this good conductor, through the 2K resistor, through this good conductor, through the 1K resistor, and round back into the negative terminal of the cell. Notice that some of these blue circles have red lines and some of them don't. Some of them have many red lines and some of them have fewer. What do these red lines mean? Each red line stands for a joule of electrical energy. Notice that as these blue circles, as these groups of moving charge move through the cell, they are given energy. The cell gives the moving charge energy. That's what moves the charge. Then notice, as these moving charges move through the resistors, they lose that energy. This is a 9-volt cell, so that means that each group, each coulomb of charge, receives 9 joules of energy from the cell as they move through the cell. So the voltage at the positive terminal of the cell is 9 volt. Notice that as these charges move along the good conductor here, they don't lose any of their energy. The voltage stays 9 volt all the time. That's because a good conductor cannot remove energy, cannot remove voltage from the moving charge. But as these charges move through the 2K resistor, the amount of voltage that they have drops. It changes from 9 volt, where the charges enter the resistor, to 3 volt, where they leave the resistor. In other words, 6 volts has been lost, changed into heat energy, lost to the surroundings. Then the charges move through this good conductor between the two resistors, and the voltage doesn't change. It stays 3 volt, 3 volt, 3 volt. But as the charges move through the 1K resistor, all the voltage they still had gets lost, so that they can return to the negative terminal with 0 volts. Always charges have to return to the negative terminal with 0 volts, because the voltage, we could also call it the potential, at the negative terminal is always 0 volts. And that is one of the rules of electricity, that the charges always have to return to the negative terminal of the cell with 0 volts. It's almost like if your mother had a rule that said every morning when you leave the house, like when the charges leave the cell at the positive terminal, then you are given 9 rand. Like the charges here are given 9 volts. But by the time you come home at night, by the time the charges come back to the negative terminal, you have to have spent all that money. Like the charges have to have got rid of all that energy. So if your mother had that rule, what would you have to do in between leaving the home and coming back to the home at night? You would have to spend 9 rand. Where would you spend the 9 rand? At a shop. Similarly, the charges have to get rid of 9 volts. Where do they get rid of 9 volts? Through resistors. Now in this case, each of the charges goes through 2 resistors, the 2K and then the 1K. So they have to spend some of their money, some of their energy must be got rid of, as they move through the 2K resistor, and the rest as they move through the 1K resistor. How much voltage did they get rid of as they went through the 2K resistor? 6 volts. How much voltage did they get rid of as they went through the 1K resistor? 3 volts. 3 volts plus 6 volts equals 9 volt. The amount of voltage they were given is the same as the amount of voltage that they lose. We can write that in this equation. V in equals V out. V in is the amount of voltage that the cell gives to the charges, and V out is the amount of voltage that the resistors take away from the charges. And since there are 2 resistors in this case, V out is equal to the voltage that resistor 1 loses plus the voltage that resistor 2 loses. 6 volts plus 3 volts. Up to now, we've been speaking about the voltage at a point. We said the voltage at the positive terminal is 9 volts. The voltage at the so-called start of the 2K resistor is 9 volt. At the end of it is 3 volts. The voltage at the start of the 1K resistor is 3 volts and at the end is 0 volts. But actually, you cannot get an instrument that measures the voltage at a point. A voltmeter always measures the voltage between 2 points. That's why we place it in parallel. So it has 2 probes, 2 arms. One touches one point, the other touches the other, and then the voltmeter gives us the difference between the 2. That's why it's also called the potential difference. You can call it the voltage across a component or the potential difference across a component. So let's imagine we place a voltmeter in parallel across a cell. This cell here has 0 volts at the negative terminal, 9 volts at the positive terminal. A voltmeter feels the difference between that. 9 volt minus 0 volt is 9 volt. So the voltmeter would read 9 volt. What is the meaning of that reading? It means that that cell is giving 9 volts to the charges. It is giving 9 joules of energy to every coulomb of charge that passes through it. If we connected a voltmeter across this 2K resistor, it would feel that there are 9 volts at that point and 3 volts at that point. Subtract 9 minus 3 equals 6. And that is the reading that this voltmeter would give, 6 volts. What is the meaning of that 6 volts? It means that in between those 2 points, 6 volts has been lost out of the circuit into the surroundings. If we placed a voltmeter across the 1K resistor, it would give a reading of 3 volts. 3 volts minus 0 volts equals 3 volts. The meaning of that 3 volts is that 3 volts is lost as the charges move through the 1K resistor. Notice that there is double the voltage across the 2K resistor compared to across the 1K resistor. And that's because a 2K resistor is double as difficult as a 1K. 2K is double as resistant as 1K. I've tried to show that by showing the 2K half the thickness of the 1K. So that's meant to suggest that the charges have to squeeze through the 2K and is more difficult than when they move through the 1K, even though the 1K is more difficult than the good conductors. A better way really of looking at it is that the charges have to fight double as much as they try to struggle through the 2K resistor compared to when they struggle through the 1K resistor. They don't need to struggle at all as they go through the good conductors, but through the 1K and 2K resistors they must struggle, but they have to struggle much more, double as much, through the 2K resistor than the 1K because it's double as resistant. And because they struggle double as much through the 2K, they lose double as much voltage as they move through it compared to when they move through the 1K. That's why the voltage lost as the charges move through the 2K is double as much as through the 1K, 6 volts compared to 3 volts. However, the current strength is the same through all parts of the series circuit. I1 equals I2 equals I3. They all move just as fast wherever they are in the circuit. There's no part of the circuit where they're moving faster than another part. Even though at some places they have more energy than at other places, that doesn't matter. they all move at the same rate.